Hello, everybody. Thank you for coming. My name is Dmitry Levin. I am the chief software architect at Basalt, where we do GNU Linux operating system. But I'm also the maintainer of strace for the last, slightly more than last 10 years. So today I'll be talking about postmodern strace. What is postmodern strace? I used to talk about modern strace last year, so I understood that I can't name it modern strace any longer if I'm talking about very recent features. So where traditional strace ends and modern strace begins, and when modern strace ends, well, modern strace never ends. So when it turns into postmodern, well, it's kind of subjective. So, well, my definition is very simple, that the strace that was before I started maintaining it is traditional, and all the rest is modern. And yeah, so here it goes. And well, postmodern is all new features since the last talk at FOSDEM. So I'll be covering mostly what have changed for the last 2 years. But I'll remind you briefly about traditional features just to refresh these features in your memory. So strace is a mostly Linux system call tracer. It also can not just trace but tamper the system calls since like several years ago. But it has a lot of options to control its behavior in different ways, like whether it prints instruction pointers, whether it prints timestamps or not, how it prints strings, what system calls are printed and which way they are printed, what's abbreviated and what's not. There are also options to control what signals are printed. It can also dump the data that goes through descriptors. It can print its output in different ways. So you can, for example, redirect it into a pipe or collect output for each process separately. Yeah, a lot of features that control what syscalls would be printed. It can also print statistics on system call invocations. It can attach to already existing processes. It can follow forks, and it can don't follow forks, depending on whether you specify the option. Well, that was traditional. There were also quite a few options added for the last 10 years. Like you can print a lot of details about descriptors, like what paths are associated with them, or what socket information is behind sockets when these descriptors are sockets. We can print stack of user function calls. Yeah, you can filter system calls by path names. We finally got support for regular expressions for filtering system calls. So you can specify which syscalls are printed using regular expressions and so on. Yeah, more ways to control how statistics is printed, how it's traced. So you can, for example, attach to many processes. You can run a strace as a detached process, and so on and so on. Well, and there's also this big feature which changed strace. I mean, it changed not just the strace, but the way how people look at it. It's system call tampering. So you can not just trace system calls, but also inject various things, like starting with return code. Also, you can inject signals and delays. But this all was more or less covered in the previous talk. So in the last 2 years, we got ptrace get syscall info support. It went both into the kernel and into strace. We got system call return status filtering. We have seccomp assisted syscall filter nowadays. There are also a lot of new system calls in the kernel that are supported. and we have more and more elaborated system call parsers. We also finally have long options. Yeah, we had no choice. We will soon see why. And finally, a bit more than a year ago, we changed our BSD style licenses to a copyleft license. So let's start with the first feature. Well, the story itself started very long, like I think it was 2001. Then this new architecture, it is 664, appeared. So the way it was added in Linux kernel, obviously was to support both 64 and 32-bit processes for obvious reasons, because it was the main feature of this architecture compared to its competitor, that it could run legacy code. And in early years of this, there were a lot of legacy code and very little native 64-bit code. But the way it was implemented in the kernel, it allowed not just to mix instructions, but also mix system call invocations. So you could actually invoke from a native code both native 64-bit system calls, but also legacy 32-bit syscalls. And it was very poorly documented, if at all. It was very surprising to many people, and it wasn't really exposed in the kernel API. So yeah, what user space trace and debuggers could do, they could fetch the system call number. They could fetch this register that describes the bitness of process, and then they would just guess, do the wild guess, and say, well, if the process is 64-bit, then probably the syscall is also 64-bit, right? It's mostly the case. And if it's a 32-bit process, then syscall is definitely 32-bit. And all the logic depended on this wild guess. And it mostly works, because in most cases it's exactly what happens. But sometimes it's not the case. And back in 2008, there was a bug report against strace in Debian architecture. There is a very simple example that looks, you can see, are very similar to it. It's somewhat simplified compared to the one reported in that bug report. So the program does a very simple thing. It just prints a line of output. And then it invokes a 32-bit system call. And then it prints another line of output. But this 32-bit syscall is actually a fork. So what happens is that there are two processes, and each of them prints the line. So if you compile link and run this program, you'll see an output similar to this. Maybe P numbers will change, but all the rest will be just very simple. But if you run this very simple program under strace, you will see something very strange. So you will see this line is being printed, and then suddenly a process attaches, and then you see this ridiculous open system call with very odd, very impossible, I would say, arguments. But all you can say about this is what? And all the rest looks very usual and regular, making the whole picture completely ridiculous. Like this ridiculous open among all nice expected system calls. So yeah, if you run this program several times, you will see that all these odd open flags are different. You will never see the same combination, or probably never see the same combination of flags, because nowadays, thanks to kernel address randomization, all these registers contain garbage that changes. And this reminds me of a toy I had in my childhood, a kaleidoscope. you turn it slightly, and you see a different nice picture. So you can use this simple program as a kaleidoscope, if you like. Yeah, so this problem was approached several times, but until 2018, there was no progress. And finally, well, thanks to two people who contributed this API in the kernel, and there are two authors and 20 more people who reviewed this, and added bias, added silent bias. It took us almost 9 months to get this into the kernel, and don't remember how many iterations, but it was 2-digit number of iterations. So finally, we have it in the kernel, and for all architectures that support trace hooks, which are all supported architectures, or almost all, I would say, and some that are not supported but get it for free. We have this, and yeah, the API looks this way. There is a structure you can request from the kernel. It contains this crucial architecture field, and in other ways it looks similar to seccomp data. So you can obtain in one go both the architecture, the syscall number, syscall arguments, also instruction pointer, stamp pointer, and this makes traces that use this API reliable in this respect, in respect to the original problem. So the same program now looks if Linux is fresh enough and the strace is fresh enough, you see this is as expected. So process attaches, you see a proper fork call and not this ridiculous open, and all looks good. So I think other traces and debuggers that have something to do with system calls should switch to this API. By the way, it also allows to find out what kind of ptrace stop is the current stop. Otherwise, up to this time, kernel provided no way to find out. So they used to think that they alternate. So first you enter syscall and then exit syscall, but it's not always the case. So you actually can use this nice API to find out and what is actually the ptrace stop you're dealing with. Okay, so it was a very major feature for strace, and yeah, as I said, some other traces are welcome to use this, of course. Let's speak about system call filtering. There is a new option to filter system calls by return status. It had a very unusual history for strace. So it was actually introduced in 2002, but it was broken from the beginning. It was never announced. You couldn't find it exists unless you accidentally type it in or look into the source code, because it was broken. So what it did, it printed the beginning of system call, and when it failed, it just didn't print the ending. It wasn't useful. But now you can filter system calls by return status. So you can print only those system calls that are succeeded or those that are failed. So in this very simple example, you can see the difference. Well, if you run a very simple program like cat with a modified LD library path, it makes a dynamic linker to look into different places. I wonder whether you expect dynamic linker to look into so many different places. But well, you can see the difference. As a very useful side effect of this option, you can have an aggregation for free. So for example, if you trace several processes that are running asynchronously, and then you will see a lot of this unfinished and resumed stuff. And sometimes it's not very convenient. We used to implement special aggregators to collect this data so it would look like this. But now, you can use this option also to aggregate. The only need, I would say, is that it might change the order of invocations. So in this example, it looks like if nanosleep syscalls were invoked sequentially, which is definitely not the case. They were invoked simultaneously, but because they were printed at the moment they finished these system calls, it looks not the way you are used to. But then when you're aggregating, it doesn't really matter in which order they are printed. So there is also another option that there is a funny story connected with it. So when I tried to come up with something useful as an example, I started invoking all programs I had in my small chroot, and I found out a few programs that were not printing their arguments correctly. Then they couldn't find them. I just invoked programs with a non-existing file. Yeah, and I found 2 of these programs in LFutils, and I fixed them. But you can get an idea when this could be useful. For example, when program doesn't print what's going on, you can like trace and have a look. When you are filtering system calls, you probably don't want to. If you don't want to print all the rest, you probably want to make those system calls you are not printing execute faster. And now we have a very nice feature, which we planned for several years, but couldn't get until we had 2 GSOC Google Summer Code students. In the year before last, the student made a prototype, and last year we had a student who is going to talk about this feature very soon, I hope. So he will describe how it works. But from user perspective, it looks like strace is no longer delays everything by 2 orders of magnitude on those system calls that are not traced. So in this, it's a famous example because this is a modification of example BPF people use to describe how slow a strace is. And now we use the BPF stuff to show how fast a strace is. So you can see that BPF itself slows down things about 10%, which is nothing compared to what all these trace stops do with speed of running programs. You can see this is a long option, and it was actually the first option that we couldn't find a good short analog. So we had quite a few, not as many as LS program has, but quite a few options, and some of them are not obvious. And we had I think, what is it, -n is in our prototype, but we couldn't find an explanation why it should be called -n. So we decided that it's time to introduce long options. And now we started adding aliases for not so obvious names. So CCOMPP was the first one. Another option which should probably have a long option analog and is the option that has name -k. I don't know why it's called -k. It prints a stack of user calls at the time of system call invocation. It's a very useful thing because you can see the logic that behind the program. If you don't know what's going on, you can just apply this. It will produce a lot of output, but it makes a strace somewhat kind of debugger more than a tracer. So in this example, you can see why for example, cat clauses stood out. From names of these functions, you can see that it does some kind of exit handling. And it closes it out to ensure that everything is written. Otherwise, it should return non-zero exit code. Another option, you can attach, you can use a strace as a detached process. So because the strace affects traces in different ways, it's not always desirable. For example, if these processes interact with their parents and they want to know their PID numbers, so you can run a strace this way and be more transparent. Yeah, there is also a relatively new option that says how all these symbolic constants should be printed. So you can print as usual, like translate these numbers into symbolic names. So you can print both symbolic numbers and raw numbers, or just raw numbers. It has like various useful implications. You can debug programs that you suspect you pass arguments to system calls in a wrong way, which is not very surprising because on different architectures there are different system call, different ABIs, the different number and order of passing system call arguments. And this also can be used. I think it's used in syscaller project. So yeah, we added support for all new system calls that were added into the Linux kernel, and nowadays they started adding system calls again. So yeah, like bunch of new system calls that work with mount points. But well, I can't describe them all. There are too many. You should ever look into man pages probably. But we have support for them. We also have a lot of very sophisticated system call parsers. And I'll show you an example which looks very monstrous, but you will get the idea how sophisticated system call parsers could be. So we support decoding of netlink protocol. And you can see this output. This is the output of a very simple routing table. And here you can see what's going behind. Yep. So you see this netlink protocol is very structured. It has some structures, substructures, sub-substructures, and everything is printed. Coloring is mine. All the rest is made by strace. Yeah, and the last but not least is that in December of 2018, we changed the license. So strace used to be released since the very beginning under Berkeley style license. So it was by request of Paul Kreinbuch. I don't know this man. It was too early. So when we added support for ptrace getsyscallinfo API, it was kind of crucial point. Most contributors to strace didn't want to contribute under permissive license any longer, so we decided we would rather change to copyleft. So test suite is released under GNU GPL v2+, and all the rest is a license that allow us to release this as a library someday in the future if we manage to make a library out of strace. Yeah. So this is more or less what I wanted to talk about. And if you have some questions or ideas or something related to strace to discuss, we have some time. Yeah. Should I repeat the question? So please be concise. Should I pick? Yeah, from the back to the front. Yeah.
Yeah, so you mentioned this proof of feature that speeds up filtering processes calls so much. So why isn't it actually default? And we have to actually put it the long argument to use it.
So the question was why this compile system call filtering is not by default, and why you have to type this very long option to use this feature. First of all, you can abbreviate long options, so you don't have to type that much. I think 2 letters is usually enough. If not, then type 3 letters. Some shells allow expansions of program arguments, so I don't think this is a problem. But well, there are 2 important points about this way of filtering. Is first, it generates and attaches a BPF program. I'm not going to dive into details, but it makes this program, and you can attach it, but you can't get rid of it unless you're privileged. So this implies that you have to follow forks. You have to follow all processes that are forked by the process you are tracing. And this kind of change behavior. And one of important points of a strace is that a strace is backwards compatible. So we can't enable follow forks by default because people are not used to this. Yeah. And if you specify this option and do not specify follow forks, it says that I'm enabling follow forks. Hey. So this is one point. Another point is that unless you are privileged, and a strace is used as a privileged program, you can't attach a BPF program to another process. So you can attach to a process using ptrace sys or ptrace attach, but you can't attach a BPF program to another process. You can only attach a BPF program to yourself. So one of important features of a strace is to trace already existing process wouldn't work with this, unless you're privileged. But if you're privileged, you can use a lot of kernel tracing nowadays. It's not really a big deal, although they don't have so elaborate traces. Yeah, please, another question. Yes?
So you mentioned that on the last slide that the color was your own. Would you consider adding color output to strace?
So the question was that on this slide, the color was my own, and would I consider coloring by a strace? It's kind of, this is a difficult question because we had actually a plan to generate a structured output from a strace. And if you generate, for example, some JSON output, you would apply already existing software to do all this fancy stuff like coloring. So we decided we will make structured output first, and then other people will do whatever coloring they like. But as you can see, there is no structured output yet, and I have to do all the coloring. Yes, please.
Could you pretty print that?
Sorry?
Could you pretty print that with the indentation of new lines and things?
Me?
No.
I think I can. So the question was whether I can pretty print this. I think this is pretty enough. So what was your question?
Well, just saying it's like quite hard to read a block of text like that, broken into rich
so-
structure and things. It's easy to read.
Whether I can print this in blocks so it'll be easy to read. Yeah, it's getting closer and closer to our idea of structured output. So yeah, you can see why we decided to go the simple way, but it was not so simple. Is it over?
Yes.
Okay, thank you for coming.